Okay, welcome back, everybody. I will start a new topic right now. Basically, uh, this was the plan for this today, but because of some because I needed to cover something I missed the last 2 days. I'm starting this a bit late, but anyways, I hope to finish this in 1 hour. And basically, I want to now talk. I talked about civil works. Now I want to talk about the hydroelectrical machines. That also is an important part of uh, any hydropower project, mini hydro projects. So basically, I'll talk about two things: hydraulic turbines, generators, and powerhouse. I'll focus a little bit more on hydraulic turbines rather than generators and powerhouse. But of course, these are also all very important parts of the hydropower project. As you know, hydraulic turbines are hydraulic machines that convert hydraulic energy to mechanical energy. Okay, so basically, the uh, turbines, the mechanical energy is then uh, is transferred to the generator, which will now then convert the mechanical energy into electrical energy. And this is on the right, you have what is known as a Francis turbine, where the lower portion is the turbine and there is a shaft which is connected from the turbine. This shaft movements, the mechanical movement is then using magnetic and electrical. I'm not an expert on generators, but basically they use the rotors and the poles to generate, convert that into electrical energy. Now, the hydraulic turbine part, basically it has what is known as a runner, the wheels, and this water, the kinetic energy, the potential energy of the water is converted into kinetic energy. And this then turns the blades of the turbines in an efficient way, the runners to sort of uh, uh, produce mechanical energy from the energy that from the water flow energy. Hydraulic energy is the energy, the potential, the potential energy is converted into kinetic energy, and this kinetic energy is in the turbine converted into mechanical energy, and the generator converts the mechanical energy into electrical energy. Okay, so basically hydro turbines has the runners, then they have the guiding vanes, the apparatus that will direct the water to the inlet in a specified direction. So the turbine design is basically using the most efficient way of this kinetic energy to convert into mechanical energy. And this is in a way a mature technology because it's been there for many, many years, since the early 1900 and late. In fact, the Francis turbine was patented in 1849. So it's been there for a while. So the main types of turbines used in hydropower are the Francis turbine, which was patented by engineer named Francis in 1849, a very long time back. Then the other one is the Pelton turbine, also late 1800s. And um, uh, uh, see, there is somebody entering there. I want to make sure he's off. Okay. Uh, and the other one is the Pelton turbine, then patented by Pelton. Then we have the propeller turbine and Kaplan turbine, patented by Kaplan, very old. The Darier's turbine is a new diagonal turbine suitable for 20 to 100 meter. Then you have turbo impulse wheels for small projects less than 10 megawatts. Okay. So basically you have the Pelton, the Francis, the Kaplan. So I'll give you some examples of these turbines a little later. Give me 1 minute. Okay. And now, in terms of classification of the turbines, uh, there are basically two types of turbines, as you must have. You must be knowing. One is the impulse, a velocity turbine, examples of which are Pelton turbo turbines. Other is the reaction or pressure turbines, which are uh, just a moment. Let me. I think there's. I need to. Sorry, just a moment. Yeah. So we have the impulse and the reaction. Uh, Sorry, just give me a minute. There is some echo, so I need. Hmm, okay. Yeah, I think it should be fine now.
Hello, Divas.
Yes, please. Can you hear me? Hello.
Yes, yes, we can hear you.
Okay. So there are two types.
Yeah, we can hear you.
Yeah, the impulse and the reaction turbine. And basically, in the impulse turbine, like Pelton and Turbo, basically, this is like the water uh, hits the buckets, and this is not under pressure. But the reaction turbine is all the kinetic energy is converted here. It's all not under pressure. But in reaction turbine, the casing inside this, the water is under pressure. So this is just the difference, which we will come a little later. And in terms of the direction of flow, there are different type of turbines, and this depends on the flow through the runner. Okay, so one is the tangential flow turbine, which tangentially hits the runners. Okay, and from this side, the radial flow turbines, like the Francis, it basically hits the turbine runners radially, and okay, there's an in, the tunnel rotation is in this way. Then there is this is the this is the axial flow turbines. The radial turbines are, you have a mixed flow and a normal radial flow turbine. This is the way it is created. It's from a radially, it acts the flow, the water jet hits it radially. This is axial wise, and this is by tangential wise. So depending on the direction, there is another classification of the turbines. Now, but the two important, impulse turbine and reaction turbine, I think it is important to understand the basic difference. Okay, I mean, it's not. It's nowadays, actually these are modular. So once you know the head and the discharge, you can actually go to a manufacturer of these turbine and generators and ask them to give you the technical specifications with the efficiency, the speed, the runner size, everything. Okay, so uh, but it's good to understand the principles in these types of turbines. So basically, as I mentioned, in the case of just a moment, I want to do it spotlight. Okay, in the case of impulse turbine, basically all available energy is converted to kinetic energy by a nozzle. Okay, the nozzle is used, which forms a jet, and the kinetic energy hits the uh, runners. Whereas in the reaction turbines, only part of the fluid energy is transferred into kinetic energy when it enters the runner, because the runners are the casing, the turbine itself is in under pressure. Okay, blades are action when the turbine blades move when it hits the nozzle. Odd blades are action all the time. Okay, so what this means is it's like a wheel. The water, that really the kinetic energy of the water, that moves the blades. Whereas in the reaction turbine, since the turbine itself, the inside of the turbine is under pressure, all these blades are moving. And uh, so so the wheel do not run full, so not necessarily the water is filled. So there is some free access to the bucket. water completely fills the vane passage throughout the operation of the turbines. Okay, this is the reaction. Casing is, I mean, this is casing is uh, is just to prevent splashing and to guide the water in impulse. In the case of reaction, it is under pressure, so you have to have the casing. So, and in the impulse turbine like Pelton, it's above the tail race water level. And in this one, this is submerged. Repair of components is easy in impulse. Repair of components is difficult in the case of reaction. Impulse turbines are used for high head, small in size, run at high speed. This is reaction for relatively low head. Pelton Turgo are impulse turbine example, and Francis Kaplan are reaction turbine example. So this is just a sort of a textbook information. Now I just want to give you an example of the Majao mini hydro project, the rehabilitation. From what I understand, I think Mr. Constantino must have provided more details on this, but I just wanted to point out that they have used, it's the head, the rated head, for example, is 17 meter. This is the design discharge and the install capacity. At the rated head and design discharge, the efficiency is 84%, okay? And they are using what is known as a cross-flow turbine, made by a company called Osberger. And this is the details, okay? And the speed of the turbine is 197 RPM, and the runaway speed is 460 RPM. I'll explain what this we mean by the runaway speed and the speed of the turbine later. Speed of the turbine is the rotational speed, rotations per minute. And one thing you notice is at the rated discharge and the head, you have the maximum efficiency, 84%. When the head decreases or the discharge decreases more than the rated head, and the head and discharge is higher than the rated head, there is a slight decrease in the efficiency. Since the difference in net head from the rated head, minimum and maximum, and the discharge is not so much, the efficiency difference is just maximum 1%. Okay, this is just to give you an example of the Majao mini hydro project. This is the information I got from the consultants of this project. Okay, and now okay, now okay, just a moment. Let me just. Okay, so now there are some factors, some parameters that needs to be understood. Okay, one is the specific speed. Specific is the speed at the machine produces 1 kilowatt under 1 meter head. Okay, so this is the specific speed, and we have uh, uh, the formula which gives you the specific speed. It's basically in 1 kilowatt in under 1 meter of head. And I mean, this is the formula used. Power in kilowatt. Let me just, I think somebody needs to be. Okay, this is the formula, and N is the speed of the actual turbine. In the case of Majao, I think the speed of the turbine was 147 RPM, and the runaway speed is 460 RPM. Okay, so now you can, using this formula, you can find the specific speed of this machine. And when the specific speed is less than 30, you have a single jet Pelton, 30 to 50 multi-jet Pelton, 50 to 260 Francis, 260 to 860, you have Kaplan. So, so you can basically calculate this and then also then we know based on that, we know the turbine type also. Then we have another parameter, which is known as the synchronous speed. This is if the turbine speed must be a synchronous speed at synchronous speed, because for turbine speed N to be synchronous, the following must be fulfilled. Okay, because we the because the electrical system has a frequency, and I think in Mozambique, the frequency is 50 hertz, frequency of, and I think Paul covered this very nicely in his lecture on basic technical features. So basically, this is the for a synchronous speed, we need to have a synchronous speed of 120. F is the frequency, and this N is the number of generator poles. So based on this number of generator poles, you get this synchronous speed. The number of poles are even number to have proper magnetic field, but nowadays you have a new trend where a multiple of 4 for better dispersion of magnetic flux is proposed. So this is slightly on the electromechanical aspects. I know a little bit, but the details can be found in the proper references. Okay, so but the other parameter of turbine that is considered is the runaway speed. In the case of the cross-flow turbine in Majau, the runaway speed is 460 RPM, and there are certain cases where the runaway speed should not be more than a certain percentage of the normal speed. Okay, so this one needs to, I don't know, I have to check. I think this is wrong. It should be, it's basically a runaway speed is the percentage of normal speed. So in our case, the normal speed of the cross-flow, the Mazau thing is 147, and the runaway speed is 466. So it's basically 230% of the normal speed. So this is around, so somewhere in between Francis and propeller Kaplan turbine. That's why you have basically the cross-flow turbine also, because I think there is some sort of the cross-flow turbines are suitable for a range between Francis and Kaplan turbines. Okay, so this is something it's important. Then there is another factor, speed of turbines, which is the speed factor, and it is the ratio of the peripheral speed of the buckets. Okay, this is the ratio of the peripheral speed of the buckets or the vanes of the nominal diameter d to the theoretical velocity of water under the effective head h acting on the turbine. The speed, this is given by these equations, and it gives you the speed factor for an impulse, Francis, and propeller turbines are given here, and basically the specific speed for different range of specific speed is given in this one, and this will give you the variation. One thing I show you here mostly is for slightly small and medium and above hydropower projects. For micro hydropower projects, mini hydro projects, like for example, we saw in Majao, the efficiency is about 83% because we are using slightly different turbine technology, cross flow and other things. So we have to be a little careful, but this is what is the range of the types of runners and the specific speed and the and the heads, okay, and the efficiency range depending on the specific speed. Okay, okay. So this is the general background and the parameters of turbines. Now I would just like to introduce you to basically the Pelton turbines, which are basically for high head plants. It's a tangential flow impulse turbine in terms of the flow, how the water is directed. You see that there is a, these are the buckets and the jets. The nozzle directs the water to these buckets so that the buckets move and moves the socket, the shaft, and the shaft is connected to the generator. It consists of a circular disc on the periphery of which a number of two lobe buckets are mounted. The main parts of the turbines are the nozzle, the runner and buckets, the casing overall, and the braking jet. Okay, and the design parameters that needs to be are important is the diameter of the wheel, diameter of the net. The diameter of the wheel is the overall wheel. The jet nozzle is the small d. The width of the bucket, the speed of the turbine, and the specific speed. So these are the design parameters which are important for Pelton. For the Francis turbine, it's basically an inward mixed flow reaction turbine. Okay, you see the water from the penstock enters the turbine casing, and then this is under pressure. So all these buckets are moving, the runners are moving. So operates on the medium head and medium quantity of water. So main parts of the Francis is the casing, the guide mechanism to guide the thing, guide the runners, the water, sorry, and the runners. And there is what is known as a draft tube. And this draft tube is needed because the pressure difference between the outlet and the inlet is high. So there is a sort of a negative pressure, something like this is created. So this has to be, so so the draft tubes are used, and the turbines can be, are placed, it can be submerged, and there is the tailwater level is here, sort of so the draft tube also helps you to gain some additional head. Okay, this is the Francis turbine. So in terms of propeller and couplant turbine is similar to Francis, are axial flow reaction, but are axial flow reaction turbines. Main parts of Francis turbine are, of course, the casing, guide vane mechanism, runner, and the draft tube. Okay, so this is a different propeller turbine, and it's mainly for lower heads and higher discharge, relatively high design discharge. As I mentioned, the reaction turbines needs a draft tube and a tube or a pipe of gradually increasing area for discharging water from the exit of the turbine to the tail race. Since pressure at outlet of reaction turbines is generally less than the atmospheric pressure, it's less than the atmospheric pressure, so we need a draft tube to sort of so that the water can flow. Otherwise, water will not flow, because if the pressure above is less than the atmospheric, so it's difficult for the water to enter the tail race. So net head is also increased because of the draft tube. So draft tubes can be of different types: conical, simple, moody, spread tube, elbow, draft tube with circular inlet, percentage, blah, blah. So these are different types of draft tubes, which we will not cover so much in detail, but I wanted to introduce you to that also. Now, the important part of any turbine characteristic is the performance. You know, basically, we are interested to see what is the performance of these turbines in terms of changes in the design discharge. Okay, the rated discharge, okay, is QG, and if the Q varies, okay, you see when the rated discharge is around 1, you get the maximum uh, uh, efficiency. But now in the case of fixed propeller, okay, this one, if the discharge available, water available is 70% of the design discharge, then you get a reduction from zero point 0.9 to zero point 0.7. So if it is very low, 4%, you cannot generate any electricity. The efficiency is almost zero. For the cross flow, there is, okay, this is the cross flow turbine that Majau is using. So the range of discharge variation up to 60%. Also, there is not much change in the efficiency. There is not much change. Hello? Okay. So you see, there is not much change in the efficiency in the cross flow type of turbine. Even in the Pelton turbine, comparatively, the changes in efficiency with terms of discharge is not much because the head is very high. Okay. And similarly, for a full Kaplan also, the change in efficiency is not high, not so much. But of course, when the available discharge is less than 30 or 40%, then there is a drastic drop in efficiency. In the case of Francis, there is a drastic drop of efficiency when it reduces from 60 to 70% of the normal design discharge. So this is an important factor when you are designing the number of turbines. For mini hydros, because we are small, talking of micro hydros, we're talking of very small uh, size turbines and generators. So the discharge variation is also expected to be not much. But for other medium and large hydros, the variation of discharge may be more. So in this case, we may need to have more than one turbines, multiple turbines, so that we manage the energy correctly. Now, to select the turbines, okay, it's very obvious that very high head plants have Pelton. Okay, if it's more than 350 meter, then you have a Pelton. So high head between 150 and 350, you could have Pelton or Francis. There are some disadvantages of Pelton and Francis. For higher speed, specific speed, Francis is more compact and economic. So this is another factor. For medium, 60 to 150 is Francis. For low head, below 60, it's Kaplan. So 30 to 60, both Kaplan and Francis could be thing, but for less than 30 meter Kaplan, less than 15 meter, it's propeller. So now if you see on the x-axis is the flow, cubic meter per second. On the y-axis is the head. So when you have very high head, this is the Pelton area, okay? Okay, and the turbo is high head and about up to 10 cubic meter per second. Okay, the Francis is from 10 to, the red one is 10 to almost 300. Okay, so you can still have Francis. So there is some overlap. Cross flow is basically, I mean, you can have from quite a big range of cross flow. Okay, and Kaplan is the blue one. Okay, the blue one also has, you can have up to 50, 60 meter, you can have Kaplan, but between 50 and 60 to 30 or 20, 30 meter, you still have Francis. So there is an overlap. So this is general criteria for the selection of the turbines. And another thing is also for micro hydro, this is something I got from the manuals for micro hydro. If you see the specific speed, so you have a, I mean, for depending on the specific speed and the head, okay? So Pelton has basically low specific speed. Francis had like below 20, 30. Francis has a specific speed around 160. Kaplan has in this range. Tubular bulb has more high specific speed, but they are for lower head. So this is also for micro hydro projects. And so because in micro hydro projects, the discharge is very small, so they did not put the value of discharge. They more dependent on the specific speed and the head. So this is some criteria. Okay, now I just wanted to give you a small demonstration exercise of the Majao mini hydro project. Okay, the Majao mini hydro project, let me just has basically okay, here the Majao mini hydro project, just a moment. Okay, the, the, the Majao mini hydro project, okay, I wanted to sort of just calculate the specific speed of the cross-flow turbine installed in Majao mini hydro project. Okay, the speed of the turbine is 197 RPM. Okay, and the rated power is 595. Okay, the efficiency is 84. The head is 17. So now, if you want to calculate the specific speed of Majao, then you have a let me show you, the specific speed of yeah, the specific speed of Majao was around 190, 139 something. Okay. Okay, using this formula, the specific speed of Majao is about 139. So, and with a specific speed of 139 based on this, and but the head is a little bit thin, so you basically also, I mean, I think that we have another selection of, if you look at the, okay, the specific speed of 139 is some sort of a, it's within the Francis sort of a range. Okay, but this is for little bit higher head. So I just wanted to show you that, let me just, sorry, that this is something that we need to take care of also. So this is how you calculate the specific speed. It also helps you understand the different parameters. But I think since I want to cover a little more today, I will not go into details, but we'll talk about it in the exercise later. And another important aspect of a design of a turbine is we need governors. Okay, basically governors regulate the rate of flow to keep the speed of the turbine constant according to the load condition. Okay, you don't want to change the speed of the turbine, because that changing the speed of the turbine will affect the generator. This is required. Yes, please.
Hello.
Yes, please.
Give us 1 minute, please. 4 seconds. Maybe it would be better you go a bit back. Yeah.
Okay. Okay, can you hear me now?
Can you hear me?
Yes, I can hear you. Yes, please.
Divas?
Yes, please.
No, yes, we have lost you a bit. Can you reverse it, please?
Okay, sorry. Okay, maybe.
Okay.
Okay, here, sorry. The performance of the turbines depends. This is important. Is, you see, when in the x-axis we have the ratio of available discharge and the rated discharge. The turbine is designed for Q0 is the discharge. At this rated discharge, you get 80 or 90% efficiency. If the discharge available is decreases, the efficiency also decreases. Okay, so we have to be careful on if there is a very high variation of river flows, then we need to select more than one units of the turbines so that the efficiency of generation is maintained. So this is one important performance characteristic of turbines. And now, regarding the selection of the turbines, we told you that for high head, Pelton is good. For medium head, Francis is used. And for low head, Kaplan is used. And for very low head, you have Archimedes, you have other types of plants, turbines. And for very like you have cross flow in the according to this is up to 10 or something. But in our case, Majau has 17-meter head, and we are using a cross flow because of the discharge also. This. So turbine selection depends on the flow, design discharge, and the head. And these are the various just guidelines for the selection of turbines, because this will give you the most economic uh, turbine in terms of efficiency, in terms of operation. Okay. And the other selection for micro hydro is also because for micro hydro, the design discharge is normally small. You don't have a very large discharge, but your head variation is also can be quite high. So this is also this one was based on selection of turbine was based on head and flow, but now we have a specific speed and head. So according to the head, different specific speed, what is the type of uh, turbines that is selected. So this is the general background from thing. This was one exercise I wanted to do, but because time is little bit running out, I want to cover today before I close. I will leave this for you to practice at home, and then you calculate the specific speed of the Majau cross flow. The information is provided here. Also, the runaway speed should be a certain percentage of, it should not exceed more than a certain percentage of the speed of the turbine. So I want you to also have a look at that one. But I will not go into the detail right now. Later on in the practice, we will do some exercise on turbine selection and the key parameters of the turbines. Now, the governors are an important part of the turbine because this governors helps to control the rate of flow. Okay, the flow, because you want to you want to make sure the speed of the turbine is constant, because the turbine is connected to the electric generator, and which is, let me just so the turbine is connected to the electric generator. So which is the electric generator needs to connect is to run at a constant speed under fluctuating load condition. So the power frequency is constant. So you need the speed of the turbine to be constant. And this speed of the turbine is controlled by regulating the flow, the governors for different conditions. For Pelton turbines, the governor decreases or increases the outlet area of the nozzle by moving the needle valve. For Francis and Kaplan, by changing the wicket gate. So basically, governors are used in turbines to make sure that we change the rate of flow to make sure the speed of the turbine is constant according to the load conditions, because to make sure the frequency of the electric supply power generation is constant, which is 50 hertz in basic principle. Okay, and so then this is the turbine section. Now, what are generators? I just briefly explain what generators are and what it does and what are types of generators we have. Okay, I will not go into the details of generators because these are information are available in standard manuals of suppliers. Generators basically transform mechanical energy into electrical energy. There are basically two types of generators. One is known as the synchronous generator. The other is called asynchronous generator. Synchronous generator are basically, can be only used for isolated grids, but they are more expensive because they have an DC excitation system, what is known, which with associated with the voltage regulator to provide voltage and phase angle control before the generators are connected to that grid. So this is what is known as the synchronous generator. But asynchronous generator means it's grid connected, so so it cannot, because the grid supplies the what is known as the excitement current from the grid, and these are the two types of generators. But asynchronous generators are grid connected. Synchronous generators can also run isolated connections. Regarding generators, I will just give you that information during the exercise. We may talk a little bit more on that. Now, the last part of electromechanical thing is the powerhouse. Okay, the powerhouse dimension of the powerhouse depends on the equipment, the number of units of turbines and generators, and the size of the turbines and generators. And so you need basically an operating quarter. You have a control and switch yards and the location of the turbine and generator. There is only one valve here. This is for a penstock thing. When you have a situation of a reaction turbine, then the layout of the powerhouse is slightly different. Okay, so this is basically for one example of a typical powerhouse with a turbine that is placed in turbine and one unit of turbine and generator. This is the Majao thing. I have the drawings that I received from the consultants. I think we can do that. So what I just wanted to point out that they're using a cross flow. There is a draft tube here. This is the draft tube that sits on the above the tailwater level. And basically the head difference is between the tailwater level and the intake level. So these are different angles, different sides of the powerhouse of the Majao powerhouse, which this is the penstock that comes here, and this runs the cross flow turbines here. Okay, and I think this is the other side of the turbines. Actually, the pictures were not so good, but I think the details are available with Funai, and if you are interested, you could look at it in more detail there. Basically, my presentation for the electromechanical equipment was till here. Basically, I just wanted to introduce you different types of turbines, different parameters that we need to calculate for the turbines, and the efficiency of the turbines, the selection of the turbines. But I would tell you that these turbines are suppliers. Once you know your head available, net head available, your discharge available, then you can go to a turbine manufacturer and do a shopping, get the technical specifications of different turbine types and generators, and then do your evaluation to install in your particular project.